One of the great things about being able to work in a university environment is that there's an expectation, a requirement really, that you do experimental testing as well to make sure that what you're doing is not just theoretical nonsense. It's relatively easy to come up with a new theory. It's hard to come up with a theory that's right. And the only way to know if it's right, because we're using the principles of science, is to test it. If the theory says nothing unexpected, it's not a very interesting theory, or it means you don't really have a problem in the first place to look at. If your theory is that things fall when you let go of them, good theory. If you say they fall at a certain rate, we can test that. And so if we're able to make predictions with the theories we have to then prove that we're right, or change the theory. And so therefore, the structures lab, which we'll be seeing, behind me is the structures lab, and we do experiments in there where we'll design a particular specimen, knowing what we think is supposed to happen, and then test it to see what actually happens. And if we're right, we feel good. If we're wrong, it's even more exciting, because then we discover something new that we didn't know before. Welcome to the University of Toronto Structures Lab. This is one of two of the structures labs we have here at U of T. You can see we have a 3-story space with a crane bay over the whole length here, and then down to the distance, perhaps you can see there's actually going to be more of the lab there as well. Now, the structures facilities here at the University of Toronto started really in the early 1920s, with early experiments being done in a different building called the Little Red Schoolhouse, and those experiments were done on torsion and other mechanical behaviors. We then moved into other experiments. The first pre-stressed concrete beam in Canada was tested here in Toronto in the 1930s by Mark Huggins. And then going through in the 1950s, we had a huge expansion of the experimental work, partly late 50s, early 60s as a result of Sputnik. The Soviet Union launched a satellite over the heads of all the world and scared the pants off everybody. And as a result, there was a great investment in science and technology, including a big extension of engineering in general. So the Galbraith building was built as a result of that to a large extent. And there was a professor here in the 1960s named Connie who tested over 800 beams in a less than a 10-year period. Astounding the amount of work that he did. Those experiments are still very valuable and still requested around the world. Following through the 1970s, there were experiments done here that related to the CN Towers construction and operation. Through the 1980s, there were experiments done concerning the Rogers Centre, originally called the Sky Dome. Through the 1990s, experiments were done relating to offshore oil platforms. And now in the 2000s, we're looking at experiments relating to new materials like glass reinforcement, other structural components from individual structures around the world, and again, trying to better understand just how concrete and steel structures behave in terms of making our models match reality, because the experiments are expensive. The modeling is inexpensive, but they've got to match. And so what we'll do is we'll use the model to explain how something works and then do this experiment to make sure that it's actually correct. So it means that when we're doing things in the structures lab, we get a great opportunity because we can build something and then we're supposed to break it, which is great, because that means we learn a lot from breaking things actually. Many of us when we were young did that as well, but now we can do it experimentally and with great precision, which is also very satisfying. We are here looking at one of the pieces of equipment that is used by my students and other students as well, Professor Vecchio and Professor Collins also. What we have here is what's called the panel tester. This is a particular instrument that allows us to test pieces of reinforced concrete that are in the shape of a diamond, which fit into the hole right there. Right now, we don't actually have a specimen in there right now because we're between tests. But by looking at the back of the panel tester, we can see all the hydraulic lines where we actually provide access to all the individual jacks that can move these steel actuator arms. We also have a whole bunch of instrumentation that's in between being put into place. Now, what do we test in this machine is actually available over here. This is the previous specimen that we tested. This is a reinforced concrete panel. Basically, you can see there's a single crack along that location. This particular specimen was done looking into aggregate interlock, which is roughness on a crack. So the specimen was in the machine previously, just yesterday actually, tensioned in this way until it cracked, and then slid by putting it in pure shear. And the goal is to investigate what the shear resistance along that cracked surface is, and to see whether or not it is what we expect it to be or not. It turns out it was significantly less than we thought it was going to be, which is consistent with our expectations. We knew that it was going to be, we're overestimating things. And so this specimen allows us to better get a sense of that. This is another machine we have in the Sanford Fleming lab here. You can see what this is an MTS individual universal testing machine with a 2-meter clearance between the two big legs. In this test frame right now, we have a particular form of damper to absorb energy. This is work done by Professor Christopoulos with his postdoc Mike Gray right now. And as the testing machine goes forwards and backwards, what will happen is that the fingers that are visible connecting the top and bottom together will bend back and forth and absorb energy. And this energy absorbance can make a structure work much, much better in the event of an earthquake. You can also see beside it is our new three-dimensional scanning equipment. This is a camera that takes three-dimensional images of the surface of the specimen with wired targets to tell us the coordinates of those targets. A great new toy that has now become one of the most popular bits of equipment in the lab. Behind it, you can see in blue, there's a horizontal beam with large actuators connected to it with vertical blue columns as well. And what's missing is the diagonal component, which is the diagonal brace that would be tested. What that blue setup is the first story of a building, whereby it can go back and forth like this, and thereby engage the diagonal brace in the way it would in an actual building. In front of the blue frame, we can see a series of 1, 2, 3, 4, 5, 6 concrete slabs. Those slabs have been cast in preparation for later testing. They are reinforced with glass reinforced bars, and this is a way we can put reinforcement into a slab that cannot corrode, but it also has the ability to be very brittle in the way it fails. And so if we should use more FRP or not is an important question. And I think we're learning a lot more about this, and it turns out from a corrosion perspective the answer is yes. What we have here in red is the University of Toronto column tester. There's no specimen in it right now because we're between tests. You can see that there is a yellow jack on the left-hand side which applies an axial compression to squeeze a column along its length. And then there's the vertical jack connected to it as well, which provides excursions of lateral displacements. And this will cause the column to fail in an earthquake-like environment. And so this machine has recently been upgraded in US units to allow 2 million pounds of compression and large lateral excursions as well. And this is the work of Professor Shake. So welcome to the second of the two structures labs we have here at the University of Toronto. This is the Galbraith Lab, the Mark Huggins Lab, which was named after the professor who was involved here in the 1960s. We can see here this is the second 3-story crane bay with a 10-ton crane. And we have a strong floor under my feet right here that will hold all the pieces together. Right now we have a fair amount of open space because we managed to finish off a bunch of tests, and therefore we're preparing for new ones. Now, the things we have inside the lab here include the shell element tester over here to the right. And this is one of the machines that I'm doing a lot of work with recently. What we have is a large blue steel frame, and inside the frame we have a series of black jacks that allow us to apply forces to a concrete specimen that would be presented up in the very center. Now, the last specimen was tested yesterday, and we have the specimen out already in preparation to put a new one in. And as we're on top, I'll show you how the thing actually can work in terms of how the loads are applied and how the specimens will fail. Then afterwards, we'll look at one of the specimens that previously has failed to get some sense about what how they look after they've actually broken. Here we are up on the shell element tester, up on the platform. The specimen would go right here, and the yellow yokes that are connected to it, which we saw previously, would connect into these individual jacks, each one of which is tied in with its own hydraulic lines, its own servo connection to allow us to control independently the displacement or the force, or a combination of both. And so, for example, this and this actuator would all connect into one yellow plate that would stick right here, and the concrete specimen would be inside. We're seeing the facility right now with the jaws opened up with nothing in it. And so therefore it's sort of a monster with its mouth open but with nothing in it yet. But at the same time, it looks even more impressive when there's a specimen inside it. Now what happens is each one of these jacks can apply a force which is a push or pull force. So if they both pull the same way, it provides tension. Both push in the same way, it provides compression. Go in opposite ways, it provides bending. And then with the out-of-plane one as well, it allows the whole thing then to go forwards and backwards. This allows us to apply any combination of shear, moment, and axial load to this setup we have right here. And this is true actually for all 20 of the outside planes. This means the concrete specimen inside can handle any of the 8 combinations of stresses that a finite element can be exposed to. And when applied in a full-scale behavior, we get a much better sense of what the overall behavior of the cracked reinforced concrete is. So the type of specimens we test in the shell element tester are what we call shell elements. It's one of them right here actually. It's in US units, 64 inches by 64 inches by a particular thickness. You can see it's been painted white, and this particular specimen has already failed. What we have is a collection of steel plates that are bolted onto the outside using high-strength bolts, and this allows us to have a total of 20 different locations around the outside that we can apply our forces to. Each one of which has 3 different locations to apply a force, giving us a total of 60 actuators to control this one particular specimen. This gives us great flexibility in terms of how it behaves, and it allows us to better understand the behavior of cracked reinforced concrete than is otherwise possible. You can also see this is full scale. This is representing a thickness of a wall, and the thickness of the wall is that thick. So we're looking at large scale, which is very important, as we found, researchers have found around the world over the past 50 years really, that there's a size effect. That is, when you double the size of something, you don't necessarily double the strength. And larger things fail at slightly smaller stresses than small things do. This can seriously influence the safety we have, because historically we've done small specimen experiments because they cost less, but it turns out the behavior isn't the same as a large scale. So as a result, we're having to do specimens that are essentially full scale. And this is what we have right here.